Welcome to this video on an introduction to probability. After watching this video, you will be able to define probability, explain why we study probability, state the range of values for probability, state the probability of an impossible event and a certain event, explain the law of large numbers, and explain the gambler's fallacy, the law of small numbers, and insensitivity to sample size. What is probability? According to textbook author Sullivan, probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. He also states that the probability is the long-term proportion in which a certain outcome is observed. Why do we study probability? Why do so many people spend so much time studying probability? The answer is that people want to be able to predict the future, or at the very least, make educated and informed decisions based on what may occur in the future. Can you think of specific examples where probability would be important? Pause the video, write down your answers, and then unpause it to see if you are correct. One of many applications of probability is to ensure safety. When designing anything from bridges to elevators to cars, engineers must make sure that the probability of failure is low enough to make using such devices on a daily basis a reasonable risk. The probability spectrum. All probabilities are values between 0 and 1, or 0 and 100%. If an event is impossible, we say that the probability of it occurring is 0%. If an event is certain to occur, we say that it has a probability of 100%. Most events are neither impossible or certain, so the probability of most events is somewhere between 0 and 100%. For example, when flipping a fair coin, the probability of getting heads or tails is 50%. Fractions, decimals, and percents are all equally valid ways to express the probability of an event. On the last slide, we used percents to represent our probabilities. We could also use decimals, so we would have 0, 0.50, and 1, and we could also have used fractions. So we would have 0 out of 2, 1 out of 2, and 2 out of 2, or 1. Probabilities, again, may be represented as fractions, decimals, or percents. For example, 75% can also be expressed as 0.75 or 3 over 4. In this course, it is expected that you know how to convert among fractions, decimals, and percents. Here's an example of the sort of conversion you might be expected to do. It says, express the probability of 5/12 as a percent and a decimal. Pause this video, see if you can do this, and then unpause the video to check yourself. 5/12 is about 0.42 or 42%. Here's another example. Again, I will read the example to you. Pause the video, see if you can convert the probability, and then unpause the video to check yourself. This example says, express the probability of 34% as a fraction and a decimal. If you said that 34% is 34 over 100, which reduces to 17 over 50, you are correct. 34% as a decimal is 0.34. If you are not comfortable with this process or with the process of rounding decimals or percents, please take time to watch the videos that your instructor will provide for you on these skills. How do statisticians define an unusual event? Think first for a moment how you would define an unusual event in your own life. Pause this video, write down your thoughts, and then unpause the video. Statisticians define an unusual event as an event that has a low probability of occurring. So in other words, we would expect the probability to be small, but not impossible. If we look at the probability spectrum, we're looking over here, again, close to 0, but not actually at 0. Typically, an event with a probability of less than 0.05 or 5% is considered unusual. However, it's important to understand that the cutoff point to define an unusual event is somewhat subjective and depends on the situation. Statisticians typically use cutoff points of 0.01, 0.05, and 0.10, or 1%, 5%, and 10%. Law of large numbers. Suppose we flip a coin 100 times and compute the proportion of heads observed after each toss of the coin. The first flip is tails, so the proportion of heads is 0 out of 1, or 0. We flip the coin once, and 0 of those flips have been heads. The second flip is heads, so the proportion of heads is now 1 out of 2, or 0.5. We flip the coin twice, and 1 of those flips have resulted in heads. Then the third flip is heads, so the proportion of heads is now 2/3, or 0.667. We flip the coin 3 times, and 2 of those results have been heads. In the figure below, we plot the proportion of heads versus the number of flips. Let's take a look at the graph. We say the probability of observing a head is 1/2, or 50%, or 0.5 because as we flip the coin more times, the proportion of heads tends towards 1/2. This phenomenon is referred to as the law of large numbers. So we say that probability is a measure of the long-term proportion in which a certain outcome is observed. If we repeated this experiment a second time for another 100 coin flips and graph the results, how would you expect the two graphs to compare? Pause this video, write down your thoughts, and then unpause it to see if your predictions were correct. Here's our first graph that we just saw on the previous slide. And here's the second graph. Pause the video again and see if you can see the similarities or differences between these two graphs. Did you notice that the short-term behavior of these two graphs is very different? For example, if we look at the first graph, it never dips below the probability of 0.5, whereas this graph dips below and then above and then below 50% a few times. The long-term behavior, however, of both graphs as we start approaching a large number of trials, in both of the graphs we can see that we are approaching 50%. Unfortunately, people's intuition doesn't always help them or reflect this truth. Let's find out if you have a cognitive bias. Suppose you are flipping a fair coin, which has a 50% chance of landing on heads and a 50% chance of landing on tails. You flip the coin 8 times, and every single time it lands on heads. So what is the probability of the coin landing on heads on the 9th flip? Here's your choices. A, the probability of the coin landing on heads the 9th flip is less than 50% because the coin has already landed on heads so many times. B, the probability of the coin landing on heads on the 9th flip is more than 50% because the coin clearly has a preference for landing on heads. Or C, the probability of the coin landing on heads is still 50% because the outcome of each flip is independent from all the others. Take a minute and pause this video. Write down your answer choice, A, B, or C, and then unpause the video to see if you're correct. Most people tend to say A. They think or feel that the probability of the coin landing on heads on the 9th flip is actually less than 50%. They want the coin, which we know is fair and has overall a 50% chance of landing on heads or tails, to land on tails in order to sort of balance out the fact that it's landed on heads already 8 times. This actually has a proper name, and we're going to get to it in the next slide. It's called the gambler's fallacy. But the reality of this situation is that every single trial is independent of the others. So no matter what's happened in the past or what will happen in the future, the coin still has a 50% chance of landing on heads or tails every single time you flip it. So let's talk about this gambler's fallacy. This is the false belief that if a particular event occurs more often in the past, it is less likely to happen in the future, or vice versa. For example, if it has occurred less often in the past, it now becomes more likely to happen in the future. despite the fact that each event is independent from the last. And that's important because if you're not working with independent events, then the gambler's fallacy is not relevant. In the previous example, the probability of getting heads is 50% every single time the coin is flipped because each coin flip is an independent event. However, it feels like if we've gotten 8 heads in a row, then the coin must land on tails very soon. The gambler's fallacy demonstrates an insensitivity to sample size, in which people expect that a short run of random outcomes should share the properties of a longer run. However, as we saw with the 2 graphs of the coin flips, this is simply untrue. The law of large numbers clearly states that only the long-term probability of an event can be predicted, while a single event or even a small set of trials are not reflective of long-term probability. The law of large numbers in gambling. How does the law of large numbers enable casinos to stay in business? How might a belief in the law of small numbers cause a person playing at a casino to lose money? This video does not provide an answer to these questions so that you can formulate your own response. The law of large numbers, events must be independent. It is worth mentioning that the law of large numbers only applies to events that are independent from one another. The concept of independence will be discussed more thoroughly in a later video. For now, it is sufficient to examine a counterexample. Suppose you have a single deck of cards, such as the one shown here. If you pick the ace of clubs, which is a black card, and do not replace it, then the probability that the next card you pick from the deck is black has decreased because there are now fewer black cards remaining in the deck. In this example, picking cards without replacement is an example of events which are dependent, and so the law of large numbers does not apply to this scenario. You should now be able to define probability. Remember, probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. You should be able to explain why we study probability, which is to be able to make informed decisions about the future. You should be able to state the range of values for probability, which is 0 to 1 or 0 to 100%. You should also be able to state the probability of an impossible event, which is 0, and a certain event, which is 100. Lastly, you should be able to explain the law of large numbers, as well as the gambler's fallacy, the law of small numbers, and insensitivity to sample size. If you can answer the following questions in your own words, then you probably have a good grasp on these concepts. Remember, earlier we asked, how does the law of large numbers enable casinos to stay in business? And how might a belief in the law of small numbers cause a person playing at a casino to lose money?